Nothing new here. We got 6F after finishing 6F1. This is exactly identical as to the last time you saw it. So here's what the answer is. And I wonder how much you can do this from memory. I hope a lot, because we've been practicing this. Now let's use it in our section 6.6, day 2, finding trigonometric function values. Now, this is actually the first time that the textbook asks you to use a calculator, and so I'm going to mention this for the first time in a video. But actually, we've probably already been talking about this in class, because you've had to check using your calculator before. If you want to check an answer, then from previous sections, then you've got to be making sure that you're in the right mode for your calculator, switching radians versus degrees. So this is probably nothing new for you as a student. But but this is the first time the textbook is mentioning it, so I'll mention it now in the video anyway. Tangent of 81 degrees is equal to 6.31. That's the ratio. The input is 81 degrees, the output is 6.31. So the wrong answer, if you put it in radians, would be 10 of 81 radians. As I found, I just calculated it out. It's negative 0.81. So you get the wrong answer if you're in the wrong mode. Make sure you see degrees, your calculator's in degrees. I see degrees here. The secant of 43 degrees, that's going to be the 1 over the cosine of 43. That's how you type it in. If your calculator doesn't have, like Desmos, you can actually type in SEC and it knows it's a secant function. But most calculators don't have a secant function button. So you have to take 1 and divide it by cosine of 43 degrees, and that's 1.37. Here, most calculators aren't able to distinguish degrees, minutes, and seconds. So you have to first convert it like this: the sine of 38 degrees plus 25 over 60 minutes. There's 60 minutes in an hour and 60 minutes in a degree. There's 3,600 seconds in an hour and 3,600 seconds in a degree. So you could put these numbers like this, and you can even type this directly into your calculator. You don't have to, like the shortest way to do it would be to write this out, and then boom, you get your answer. Now, going from example 10 to example 11, I notice I'm going from degrees to radians. So boom, change to radians. Make sure you can type this in directly, both in the Desmos and in most calculators, just so long as you change it's in the right mode, radians mode. The wrong answer would be 0.997. If you try and say cosine of 2 pi over 5 degrees, that's a number very close to 0 and not very far away from, not very close to like 360 degrees. So that's why it's 0.997. In any case, boom. That's what, so big idea, make sure you're in the right mode when you're using your calculator. Now check this out. Functions. We've talked about inverses before in chapter 5. We've spent all of chapter 5 talking about inverses. So I wonder what would happen if we tried to find the inverses of trig functions. So just to lay some groundwork, as a reminder, I want to say that the input is, say, it's in degrees, so the x values are in degrees, 0, 30, 45, 90, negative 15 degrees. The output is what you might call a ratio. It's a decimal. It can be a fraction. It's unitless. It has no units. 0, 0.5, 0.711, 1, or this crazy number right here. So if you were to take the inverse of these, then it would be you would interchange the input and the output. You would give it a ratio, and you'd hit enter in your calculator, and it would tell you degrees. So here, 0.71, if you take that as your input for the inverse, the output would be 45 degrees. If the input is 1, then the output is 90 degrees. And if the input is this crazy ratio right here, the output would be negative 15 degrees. And the way we write it is sine negative 1 of the input. Now, this is super confusing for a lot of students, because this is function notation, like f of negative 1. We've seen that before. The inverse of f is written as f to the negative 1. It's not an exponent, though. Don't treat it like an exponent. This doesn't mean the same thing as 1 over sine. This means this is exponential notation. This is not an exponent. This is function notation. So let's see how that works in a calculator. If you have to solve this, then what you really need to do is interchange the input and the output. To do that, to switch them around, you would take the inverse. So the inverse of this ratio will give you a degree measure. You got to make sure you're in degrees, not radians. And I want you to find out what it is. Just go ahead and type it in your calculator. You can actually use the exponent, cosine exponent -1, and the Desmos will know that it's not an exponent, but it's actually, in fact, the inverse. The inverse cosine of the ratio 0.5437 will give you a degree answer. And I'll give you a hint just to make sure you know when you're in the right ballpark. It's somewhere between 50 and 60 degrees, but I want you to figure out what it is exactly. And then we'll move on to the next page. So I'm going to drop the bomb. Here it is. All of the trig functions fail the horizontal line test. Boo. None of them are 1-to-1. So none of these, they're periodic. So they're going at every period, they fail the horizontal line test. Look at this. Here's the sine curve. And even before it hits 180 degrees, you can see it fails. You got a horizontal line, right? And then it fails here and here and here. It fails an infinite number of times because it's so periodic. So none of the inverses are going to be functions. And that's going to make things a little tricky. But not as tricky as trying to drive to my favorite national park, Joshua Tree. I've since 2009 when I first went, I've probably been there, I don't know, 20 times, 30 times. It's a wonderful place to go hiking, rock climbing. The rocks there are out of this world. They make you feel like you're on Mars, and it's just so bizarre. And then the Joshua trees themselves are just really cool. I don't think they're cacti, but whatever. J tree, I love it. Miss you, J tree. Much love. All right, so here we go. Check this out. This is the normal sine function. I'm just going to collect all of like 4 different degree measures that all have the same output. 30 is the input, the output is 0.5. 150 is the input, the output is 0.5. 390, -210. They're all graphed right here. They're at the same height of 1/2 of the y-axis. So we can see that this is not 1-to-1. They're failing the horizontal line test in a big way. So what we want to do is let me show you one more crazy thing here. If you were to interchange the x and y values for all of these, what you would do is you would flip it on over the line y equals x, just like you would in the other inverse function. And so you can see here, the inverse, when you graph it, is like this. It used to be sine of x, and then we took its inverse. And now you get this crazy graph right here that fails the vertical line test. The inverse is not a function. So what we do is, but you just did in the previous page, you just used the inverse cosine, and it's a button on your calculator, so it's going to be a function. So what we do is we basically chop off the top part here and chop off the bottom here and just use the middle part. This middle part, this in red, is what would satisfy the vertical line test. So your calculator is only going to focus on giving you these values. Technically, your calculator should, if you type in inverse sine of 0.5, your calculator should give 30, 150, 390, -210. It should give you all these values because they all work in sine. They all produce 0.5 as an input. But it's only going to give you one of them. It's only going to give you the value that's in between -90 and 90. And in that way, it can be a calculator button function. Yikes. All right, so the inverse trig function is going to take as its input the ratio and its output the degrees, but it's only going to give you one of them. It's going to give you the reference angle that we talked about last class. So if you type in inverse sine of 0.5, it'll give you 30, and it won't give you the others. It'll give you the one closest to, it'll be the reference angle. So let's solve this equation. Sine of theta is equal to 0.2812. If you want to do that, you have to interchange the input and the output, so then you can take the inverse sine of that, and that's something you type into a calculator, and you get 16.3, about 16.3 degrees. Great. However, that's not the value that they want. The textbook is going to be a little tricky about this, and they say we want not the one that the calculator gives you, but the one that's between 90 degrees and 180 degrees. like this. So what you can do is you can draw a happy unit circle. Boom, there it is. 16.3 degrees is right here, and that's awesome. But the this is also 16.3 degrees. It's also a reference angle over here. If you move, and you might say, Mr. Bergman, why not draw the one down here? But I can tell you that these two triangles have the same reference angle. They have the same 16.3 degrees right here and right here. The reference angle down here would be negative 16.3 degrees. So the same reference. So sine has the same reference angle. Notice we've dropped it's the same vertical height, These are 16.3 degrees. But now we can see that this is 180. We can find this angle right here, which is 180 minus 16.3. And it's always good to check. You can, if this is the answer, you can put it back into the sine function and make sure it works in the original equation. Sine of your answer does in fact equal 0.2812. Let's do another one of these because it's super tricky. Given the tangent of theta is equal to this crazy number, find theta between 270 and 360. Well, here you can write the equation and you can interchange the input and the output and use the inverse then. So the inverse tan of this crazy ratio will give you a degree measure. And the calculator actually says negative 80.8. Well, that's not going to be good enough for the textbook. We want something that's specifically between 270 and 360. You can't give a negative number. So you can say, drawing a unit circle, you can say that negative 80.8 is somewhere in between, in this quadrant right here. But if you added 360, then you'd get this angle right here, 279.92, and that's within the acceptable bounds that the question is asking for. Wow, that's a lot. I want you to copy the problem list and start 6F1, do the first problem, and I'll see you in class.